Hi everyone. We're going to continue our Unit 7 discussion on alkyl halide substitutions. And we are going to compare two types of substitutions. One of them is called unimolecular, the other one is called bimolecular, and there are a lot of differences between these two types of substitutions. So this is just only going to be part 1. Now, let's see, where are we going to start? On that cover page I have a disclaimer to talk about, and the disclaimer is that we are only going to focus on substitutions, and I'm going to put that at the very top. Only consider in Unit 8, we're going to see another set of reactions called eliminations that use the same starting material, and at that point we're going to have to decide which pathway the reaction will take place, or the reaction will follow. But for now, we're not going to even be concerned with that, and we shouldn't be. But for some of you who have read ahead in the chapter or retaking organic, you probably know about eliminations, but for now we're going to pretend that those don't happen. Okay? For instance, and we saw this in video 07B20, the first video I think, that if you have a alkyl halide, and let's use the base and the nucleophile that we did before, ethoxide. You could actually have two types of products. The first one is elimination. Okay, not elimination, substitution, because the ethoxide substituted for the bromine. Or we could have elimination. And I did mention how this happened in the previous video. I'm not going to do that here, but this is a substitution product. And this is the elimination product. Okay, we're not going to be worried about this. Okay, so that's my disclaimer. Because I want to go over a couple of examples to warm up, and then we're going to talk specifically about these two types of substitution. If you're wondering what the N stands for, that stands for nucleophilic. A nucleophile is going to come in and substitute for the leaving group. Let's do some examples first. The difficulty or the key to these reactions is to recognize what's the alkyl halide and what's the nucleophile. And I'm going to give you a very unusual nucleophile, one that most students are not expecting. But if you understand the concept of opposites attract, or partial negative is attracted to partial positive, or in this case full negative is attracted to partial positive. So I'm not going to put the partial bonds or the partial charges, but this carbon is partial positive because this chlorine is very electronegative and partial negative. I'm not even going to draw the mechanism. All I want us to consider is to draw the substitution product, and those are the instructions. Okay. I'm not going to even ask for this unit anymore to draw any elimination products. Okay. Elimination products typically give alkenes. So you just have to pretend that this oxygen comes in and this chlorine leaves. You got to make sure that the point of attachment is this dot. So that's one trick that I like to use, is I put a dot on the carbon that's being attacked. So this dot means and we have some options here. Okay, we had several lone pairs that could come in and form a bond between this molecule, the nucleophile, and this blue dot. So this is, again, the nucleophile. It makes more sense that the anion is a better nucleophile, because when you make a bond, this will neutralize. You notice that if I make a bond with this lone pair, oxygen with 3 bonds would be positive. Typically, you don't want to form a positive or a negatively charged product. Neutral products are typically more stable. So there's my oxygen, and you just have to copy what's attached to it. Okay. Can you tell that this was the bond that was made, right? We have the left side of the molecule and the right side, and there's your dot. Okay. Okay, so why don't you try this one? Okay, use the dot method, and make sure you know where your nucleophile is. Okay. This one's a little tricky because I'm not drawing out the lone pairs. See, the lone pairs on this molecule help me decide that this was the nucleophile and that this was the atom that was doing the attacking. Okay. So I want you to maybe draw out all the lone pairs, identify your nucleophile, and draw the product. And go ahead and pause the video, give yourself a minute or two, and then you'll double check your answer against mine. Okay, let's use all the tricks that we know. That's the carbon that's being attacked. You should know that this anion, carbanion, has a lone pair. That's the atom doing the attacking. The issue with this is that a lot of students miss the carbon when they try to attach these two pieces together. You have to draw a bond. Okay, so the bond is going to look like this. Okay, and that bond is to this carbon here. And you could draw out the letter C, or you could leave it out. Just know that it's the triple bond that's going to start right here. And I am drawing it linearly because on a triple bond, the 4 atoms near the triple bond are linear in the same line. You can always count 1, 2, 3, 4, 5. So this is 5 carbons. This is 3 carbons. There needs to be 8 carbons here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. Okay, good. So those were 2 examples where you should be able to predict the product, and this was just by coincidence or by serendipity that I picked 2 nucleophiles that I probably did not mention in a previous video. But again, if you could identify the anion and find a lone pair on that negatively charged atom, that's the one doing the attacking. Okay. We still haven't talked about the 2 different pathways, right? There's SN1, which is nucleophilic substitution unimolecular, and nucleophilic substitution bimolecular. I haven't told you if this is SN1 or SN2, or if this is SN1 or SN2. All we have done so far is to determine that we need to draw the substitution product. Okay. But before we actually look specifically at these 2 mechanisms, I do need to give you one more list, and it's a list of nucleophiles, and we're going to rank them, good and poor. And you're going to figure out what's the difference between the set of good nucleophiles versus the set of poor nucleophiles. you could almost think of this as your master list. Good nucleophiles, the halides. Particularly the two larger ones. Okay, those are good nucleophiles. Just beware that you could be given these nucleophiles as a salt. NABR, maybe Ki, etc. Okay, and it's your job to separate out the cation and to only focus on the anion, right? The anion, like we have up here, as a nucleophile. Other ones, okay, R being a general term for the rest of the molecule, so this could be methyl, ethyl, propyl, any alkyl group. Next, how about the O minuses and the RO minuses, like methyl, ethyl, propyl, oxide. We saw this one, the triple bond, anion. In the previous video, we saw nitrile. I'll draw it this way. Maybe we should know that it's the carbon that's negative, not the nitrogen. What else? Azide. And I don't know if we talked about this in the last video, but this N negative, the anion. Some books are going to list the next two as moderate, but we're fine to keep it as good. I only want two categories. So we saw this. This is called acetate. And actually that's it. Okay, so these are what I consider the good nucleophiles. What about the poor? Why is it necessary for us to know what the poor nucleophiles are? It's necessary because poor nucleophiles actually favor one of these two mechanisms. And I'm not going to tell you now, but I probably will tell you once we get into those mechanisms. Poor nucleophiles. How about this? ROH. Okay, go ahead and copy this. Yep, that's it. What do you notice about the good and the poor? Anionic, neutral. What are these in terms of cats? Let's go back to our tabby, and I don't know what this gray cat is, but see, if the orange cat is a very good nucleophile, then it's going to be pretty reactive and it's going to force out the leaving group. So it's this picture right here saying that we're using a good nucleophile. If the orange tabby is a poor nucleophile, then it's just going to wait, and it's just going to sit around until the leaving group leaves on its own. Okay, so think about that when you identify the type of nucleophile you have. This one will attack, this one will wait. Okay, so this is the cat that will attack. And this is the cat that will just sit around and wait. Okay. Alright, now that we have that list, we could go ahead and look at some mechanisms and assign them SN1 and SN2. The easiest one to take care of first is actually the SN2. Okay. There are some cats that will do SN1. We're going to look at some cats that do SN2. And where does this abbreviation come from? It's a type of substitution where the nucleophile adds, and it's what's called bimolecular. Okay. And we'll go over these terms as we look at the mechanism. Let us use... We're going to use a good nucleophile. And again, let me use this one. Okay. I automatically put a dot here, especially if I'm going to analyze what exactly is going on in the reaction. And, well, which nucleophile can I use? Let's use this one. We haven't, I don't think, used this one just yet at negative. Okay, just remember it could be sodium plus CH3S minus. There might be sodium here that you have to mentally clear out. I'm going to show you the mechanism. Before I show you the mechanism, there are a couple things that you want to do and you want to analyze before you decide whether it's SN2 or SN1. And this one, good nucleophile, so I'll write that. What about the alkyl halide? The way we can categorize the alkyl halide is primary, secondary, or tertiary. You look at the carbon that's attached to the halide and it's connected to one other carbon. You know that this is a primary carbon. That's going to be very important. The other thing you should know about primary carbons is that it's very uncrowded. Right? There's not a lot of clutter. So here's the mechanism. You're very uncrowded. You have a cat that wants to attack and push out the gray cat. That's SN2. Practice drawing the product. Okay. Can you figure out how to finish this drawing? Okay. Pause the video and try to figure out how to draw the rest of this molecule. Okay. I would just draw a bond to the S because that was your attacking atom, and we'll just put methyl like this, right? Everyone knows that that carbon at the end is this CH3 group. Why bimolecular? Okay, we have a nucleophile, we did a substitution, but what makes it bimolecular? The first thing we have to establish that is, where is the slow step? But there's only one step. So this is what's called the RDS, rate determining step. And the molecularity depends on the slow step. Okay, so we're talking about kinetics, how fast a reaction goes. And if you have one road, how fast you get to your destination is really based on that one road. Okay, so take a look at how many molecules are needed for this only step. The way that I would state it is that 2 molecules needed to go through RDS. Okay. Now, I know that seems obvious that you need these 2 molecules to do this reaction, but in SN1, you're going to see that there's only 1 molecule involved in the RDS. Okay, so just be patient with that. Let me finish up SN2. You've seen this before in general chemistry, rate equations. So the rate is equal to the constant, K, times the 2 molecules. So you could write something like concentration of the alkyl halide times the concentration of the nucleophile. Okay, that's sufficient to talk about the rate. If you think, and we're going to build up tables slowly to determine whether something's SN1 or SN2. But if you think you are SN2, that means that if you change the concentration of either of these 2 substances, you will change the rate. Okay. So for instance, if you double the alkyl halide concentration and you, I don't know, triple the nucleophile, what happens to the rate? the rate goes 6 times faster. The rate goes up 6 times. And the way you can think about that is it's a speed. So if I drive to school and I drive normally at 40 miles per hour, okay, if I double my rate, I would be driving 80 miles per hour. So the number goes up. So you know that this 6 times means that it goes faster. 6 times faster. And all I did was multiply each amount, how much it went up by. If you remember your general chemistry, you know that these are first order, right? If you double the reactant and its first order, you double the rate. But we have 2 reactants. One I doubled, one I tripled. That means that the rate will go up by 6. Okay. Let me show you, before I run out of time, SN1. Okay. This is good that we could get them both on the same page so we could have an easy comparison. And I think some of you may realize what I'm doing to kind of switch it over to SN1. Okay, did you guys catch that? The other thing that I can do to switch it over to SN1 is use a poor nucleophile. So the poor nucleophile that I want to use is, how about this one? I'm going to use something a little bit tricky. Okay. But we know that this is the alkyl halide, and it's now tertiary. See, this may seem like a lot of extra work, right, to put our annotations, but the students that are doing well in class or have done well in the past, they totally mark up their test with annotations, even though the grader is just looking at the product. I think you'll save yourself a lot of silly errors, careless errors, by using the dot and identifying what kind of alkyl halide you have and what kind of nucleophile you have. Tertiary alkyl halide, poor. Why do I say this is a poor nucleophile? Because it's neutral. And we could draw the lone pair if you want. Okay, that's your attacking atom. I'm not going to draw the mechanism just yet. The first thing I want to test you on is whether you can figure out the product based on these facts, that this is the attacker and this is the alkyl halide with the leaving group. Okay. Give yourself a minute or 2 minutes. Definitely look at your notes. See if you can fill in the single product coming from substitution. Okay. Go ahead and pause your video. Alright. Here's your dot. Here's your nucleophile. You might think that your product is this. Okay. Do you see how I got that molecule? I just attached this nitrogen via the lone pair to this dot and kicked out bromine. So we have a bromine out here. Okay, that you, for my class, you typically don't have to draw out. Okay. Shift this over. But there's something wrong here. This molecule is positive, and there's a way to make this neutral. So this actually is not the final product. This will get partial credit. But remember in the previous video, 07B20, that when we have a neutral nucleophile, I want to remove this hydrogen at some point to make the product neutral. No good, right? Your final product is this. Okay. With nitrogen, a lot of times people don't draw the bond. It's implied between the nitrogen and the single hydrogen. I remove this hydrogen maybe at the bottom, right, to make it neutral. So there is a lone pair there. And we have that. This is your final product. Okay. Alright, in the last 4 minutes, let me go over the mechanism because it is different than what we've seen before. Why is it different? It's different because our orange cat is poor. It's weak. Oops, this one right here. Do you see how it's waiting and waiting and waiting until the gray cat leaves? We're doing the same thing here. There's no orange cat in this part of the mechanism. The gray cat leaves on its own. Okay. Now, usually that happens with heat, but if you leave this empty, it just happens with time. Look what we get. You know what happens when you have a carbon with 3 bonds and no lone pairs. Carbocation plus your gray cat. So your gray cat left. Now what's happening? Your orange cat is waiting in the wings. Okay, and I'm going to snake this mechanism going down. But where's my arrow? My arrow's this now. Normally I would ask you to pause the video, but I'm running out of time. Okay. And how do we want to remove this hydrogen? Technically, you can remove this hydrogen with another nucleophile just by doing a proton transfer. But if you are worried a little bit about balancing, which you actually shouldn't be with organic, you could use this bromide, and I'll use that. That's just a lone pair on the left. Make sure your molecules are big enough so you can clearly show which bonds are being moved. And this one bond is being moved to be the lone pair. Let me get this. Okay. And like I said repeatedly, that I usually want to draw all the products at each particular step. So we did create HBr in the last step. Okay. So when I say draw all the products at each step, it's not as if I'm bringing the bromine after every single arrow. Okay. It's only what molecules do you make in that last particular step. Okay. So here's your product. Already you could contrast it with SN2 because look, SN2 has no carbocation. No carbocation. SN1 has carbocation. So there's one huge differentiator. SN1 reactions go through a carbocation. Okay. Now, the RDS is this one. The slow step is the step where the gray cat leaves. The gray cat left on its own. It didn't have any help from the orange tabby. So in this case, the rate equals just based on the concentration of the alkyl halide. That's why this is called unimolecular. It's only dependent on one molecule. Alright. If you were following my notes, the SN2 and SN1 are all on the same page. So this would be a pretty good sheet to have with you when you're doing your problems, when you're practicing your textbook problems. Okay. SN2, 2 molecules in the RDS, and SN1, 1 molecule in the RDS, and it leaves on its own to make the carbocation. Okay, in the next video we're going to look at some more differences between SN1 and SN2.